Hello. We are here today to talk about the rest of chapter 6.3, and we're specifically talking about geometric random variables and geometric distributions. So first thing we're going to do is we're going to define a geometric distribution, talk about what that looks like, and then we're going to calculate some probabilities with geometric distributions, and then we're going to describe a geometric distribution. And just like every time that we always describe any distribution, when I say describing the distribution, I'm talking about like socks. We're going to talk about the shape, the center, and the spread. So first, what is a geometric distribution? You're going to notice that this is very similar to a binomial distribution with one major difference. So if you read this in a geometric setting, we have, instead of bins, we are going to talk about bills. So the first requirement is that you have to have two possible outcomes. So it has to be binary. You're either going to have, on each trial is either going to be classified as a success or a failure. And remember, success just means that's what you're looking for. It doesn't necessarily mean that it's a good or a bad thing. You have to have independence, so each trial must be independent. And if you think back to our first binomial example that we looked at, we talked about that multiple choice quiz that you all took. There were 10 questions, and we were looking to see how many questions you got correct out of the 10. So n was a fixed number in a binomial situation. In that situation, n was 10. You all answered 10 questions, right? In the geometric distribution or the geometric setting, this is a little different because we're looking for a number. We're looking for how many trials is it going to take to obtain the first success? Or in other words, how many questions would you have to answer on that multiple choice quiz to get your first question correct? And then similar to binomial distributions, there's the same probability of success on each trial. All right, so if you meet those four qualifications or bills, then you have what we call a geometric setting. And now let's take that and apply it to random variables. So remember, the word random variable just means that we're talking about something that is like a chance process, aka it's random, and that we have only numerical outcomes, right? So if we're talking about taking a random variable x and defining it to be the number of trials required to obtain our first success, the number of trials to obtain our first success would either be 1, our first success would either happen on the first trial, the second trial, the third trial, the fourth trial, et cetera, et cetera. So it's a random variable, and it's discrete because we have as opposed to continuous. We have like a finite, accountable number of possible outcomes. So, let me go back a second. Notation, like we've always talked about, we can say now that X follows a geometric distribution, and now the only parameter we have in here is P, the probability of success, right? With a binomial distribution, we had the probability of success and we had the number of trials. In this case, we're looking for the number of trials, right? All right, so let's look at a quick example. A game consists of rolling a single die. We're interested in how many trials we will conduct until we roll a 3. Is this a geometric setting? So we're going to talk about bills, right? So it's binary because a success is getting a 3. So roll a 3. And a failure is rolling anything else. So rolling a 1, a 2, a 4, a 5, or a 6, right? So we have independence because the outcome of each roll doesn't affect the next roll, right? So the outcomes on each roll don't affect each, that should be an A. Whoops. Uh-oh. Hold on. Sorry. Each other. All right. L means we're looking for a number. We're looking for the number of trials until we roll a 3, right? And then the same probability of success. Every time I roll a die, the probability of success, or the probability of rolling a 3, is 1 out of 6, right? All right. So we want to calculate the following. So because of this, hold on. Because of this, I can say that this, yes, it is a geometric setting. So if X is the number of rolls until we get a 3, I can say that X follows a geometric distribution where the probability of success is 1 over 6, right? So just to remind you about a little bit about notation. Now let's talk about these probabilities. So you can calculate these probabilities probably off the top of your head. Geometric distributions, geometric random variables, and these probabilities are pretty kind of like intuitive. So the probability that, in other words, the probability of X is equal to 1 means what's the probability that your first roll is a 3? That's equal to 1/6, right? There's a 1/6 chance that your first roll is going to be a 3. How about the probability that X is equal to 2? In other words, that means like the probability that the first roll is not a 3, right? And then the second is a 3. And hang on one second. So I'm looking for the probability that the first is not a 3 and then the second is a 3, right? And now the important part here is that these rolls are all independent. So if they're all independent, when I have the probability of something and something else, I can multiply those individual probabilities together. So the probability that X is equal to 2 is the probability that the first is not 3. That's 5 out of 6, right? The probability that the first is not a 3 would be like a 1, 2, 4, 5, or a 6. So that's 5 out of 6 times the probability that the second is a 3. Well, that happens 1 out of every 6 times. So if I multiply these two probabilities together, 5 out of 36. So in other words, I have a failure on the first roll, and then I have a success on the second roll, right? All right, well, what about the probability that X is equal to 3? So really similarly, that's kind of like the first one. Let me just kind of summarize this a little bit here. So the first one is a failure. I'll just say first is a failure. And the second is a failure. And the third is a success. So again, because these events are independent, we can multiply 5 over 6 times 5 over 6 times 1 over 6, right? And so that is, let me grab my calculator, but that would be 25 over 216. So you're probably seeing a pattern here. If I were to ask you the probability that X is equal to 4, well, again, that would be like 3 failures. So 5 out of 6 times 5 out of 6 times 5 out of 6, and then just 1 success. There's only ever going to be 1 success because we're looking for the first success. That's the whole point of having a geometric random variable, right? So let's summarize this here. If Y has a geometric distribution with a probability P of success on each trial, the possible values of Y are 1, 2, 3, ... And think about it. We purposely don't have 0 now here as a possible value because we're talking about how many trials does it take to have your first success. So you can't have 0 trials, right? But if K is any one of these values, then the probability that Y is equal to K, that should be, is equal to 1 minus P. This is really the probability of a failure, right? So it's the probability of failure. And then if we're talking about K successes, K minus 1 is the number of failures. And then we only ever have one success, right? So we multiply the probability of failures times the number of failures, or to the number of failures, times the probability of success, just to the first power, because we only have one success. So if we put this all together, hang on, let me erase this. But if we put this all together into a probability distribution table, so X is the number of trials that it takes till I get my first success. So X could be 1, 2, 3, 4, 5, 6, et cetera, et cetera. Notice I have these like ... because theoretically I could keep, in the case of this, rolling the die example, I could keep rolling the die over and over and over and really never getting a success. I could theoretically keep rolling and rolling and rolling and never get a 3. Now, it's really unlikely, eventually I'm going to get a 3, but theoretically this would go on forever. And so you can see my probability distribution table here, all right? Okay, so here's an example. Mr. Lochelle's class decides to play the lucky day game. A student will be selected at random from your class and asked to pick a day of the week, and then your teacher's going to use technology to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class will only have one homework problem. If the student picks the wrong day, your teacher will select another student from the class at random and repeat the process. The game continues until a student correctly picks the lucky day. So Y is the number of homework problems that the class receives. Find the probability that the class receives exactly 10 homework problems as a result of playing the lucky day game. So remember, we can't ever use any of these formulas that we just talked about until we first establish that this is a geometric setting. So we have to say that X is geometric. I'm sorry, this should say Y because we defined it to be Y. So Y is geometric because it's binary. A student either picks correctly or not, right? We have independent. Each student's guesses are independent because the day was chosen randomly. L, we're looking for the first winner. And we have the same probability of success, in this case, 1 out of 7. You have a 1 out of 7 chance of guessing the correct day, right? So this is geometric. So we want the probability that exactly 10 homework problems are assigned, right? So we want the probability that Y is equal to 10. So in other words, we have 9 failures. So the probability of a failure would be 6 out of 7. And we had 9 total failures. And then eventually we had the 10th guesser was correct. So the probability of that one being correct is 1 out of 7. If you plug this into your calculator, you get 0.0357. So in other words, about like 3%. So now if we want to find the probability that Y is less than 10. So this is the same situation. Find the probability that Y is less than 10. So in other words, this is equal to the probability that Y is equal to 1 plus the probability that Y is equal to 2 plus the probability that Y equals 3, ... right? We're going to utilize this ... all the way up to the probability that Y is equal to 9. So again, you're not going to write out every piece of this formula. You're going to use those ... right? So I have the first couple terms so I can establish the pattern, and then up to the last term. So there's about a 75% chance or probability that the class will get fewer than 10 homework problems by playing the lucky day game. So I'm just going to remind you, just like we talked about with binomial random variables, no matter what you plug into the calculator, because I'm going to show you in a second how to use the calculator, no matter what goes in the calculator, you must show this formula. Back here, no matter what goes in the calculator, you must show this formula here. All right? So speaking of, let's talk about the calculator. So under second distribution, that's where we have like our normal CDF, our binom CDF. You're going to have a geomet PDF and geomet CDF. So remember, PDF points to a value, CDF accumulates area under the curve. And so if we want to answer the first question, we wanted the probability that x was equal to 10. Your probability of success is 1/7, and you're looking for x is equal to 10. So you can use your calculator to just quickly crunch the numbers for you. On the other hand, the second question, we wanted the probability that x was less than 10. Remember, when you use a CDF, it only gives you like x is less than or equal to. It only gives you less than or equal to areas. So you have to convert that into less than or equal to, and it'll give you that area as well. All right. Let's talk about mean, or in other words, expected value, standard deviation, and we're going to talk about shape as well. All right. So if you think about it, this formula hopefully will make sense to you. The mean or expected value of a geometric random variable is 1/p. So in other words, if there is a 1/6% chance or a 1/6 chance of rolling a 3 on each roll, my expected value, or in other words, the expected number of trials that it would take until I get my first 3, would be 6 rolls. And then here's the formula for standard deviation. That's a little bit less obvious, but I'm just going to ask you to trust me on that one. And then let me get out of here because I want to show you a little bit about shape. So hang on. All right. So if we have a 1/6 probability of success, kind of like rolling the die, here's what the geometric distribution is going to look like. So notice the shape. It has kind of like this strong right skew. And think about what this is saying. This is really our number of trials it takes until we roll the first 3. So there's a good chance that we roll the first 3 on the first trial or the second trial or the third trial. And then the chance of me rolling the first 3 on the 18th, I can't circle this, but on like the 18th or 21st, once you get out to the far right, the chance of me rolling 18 rolls until I get my first, 3, it's pretty small because my first 3 really should have happened like before then. Why is it not letting me? There we go. Sorry. Now, if I change this probability of success to a number like 1/2, so if there's a much greater chance of success. So for example, this would be something like maybe flipping a coin. If I'm flipping a coin and I'm looking for the first head to come up, this is going to happen much more frequently. So my distribution is still going to be extremely right skewed, but you're going to notice it tails off much quicker. Like by 6, you can see that this is like minimal probability, right? So hopefully it should make sense to you that your distributions are all going to be right skewed. So when we talk about describing the distributions, again, shape, center, spread, right? So the shape is always going to be right skewed. Always, always, no exception to that rule. The center is going to be, in this case, now we're talking about the lucky day problem again, but the center, the probability of success was 1/7. So the expected value is going to be 1 over that, or 1/7. And then the standard deviation, and you could plug this formula into the calculator, but your standard deviation is square root of 1 minus 1/7 over 1/7, which will give you that number there. And here's your interpretation. So if the class played the Lucky Day game many, many times, the number of homework problems they would receive typically varies by about 6.48 problems from that mean of 7 that we found up above. So that's socks, right? All right, here's another example problem. So a local fast food restaurant is running a draw a 3, get it free lunch promotion. So after each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from the standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer has to pay the bill. So X is the number of customers it takes to get the first free order on a given day. And remember, before we calculate any probabilities or mean or standard deviation or do anything, if I'm using these formulas, I have to say that the distribution is geometric. So let's think about it. Bills, right? So binary, we either choose a 3 or we don't, right? So success is getting a 3 or not. Independence, each card draw is independent. Again, we're assuming that the deck is reset after each trial. We're looking for how many customers it takes to get the first free order. And if we're looking for the card to be a 3, the probability of success is 4 out of 52. So X is geometric with P equal to 4 out of 52. So now that we know that it's geometric, we can use our formulas, right? So if X is geometric, the mean or the expected value of X is 1 over P. So 1 over 4 over 52, which is 13. So interpretation, if the restaurant runs this promotion on many, many, many days, the average number of customers that it takes to get the first free order would be about 13. And hopefully that should kind of make sense to you. So now we're going to look at the standard deviation. So remember, standard deviation is square root of 1 minus P over P. So you can see that we plugged in here. You're going to have to use the calculator to plug in. You get 12.49 and interpret it. So again, remember, this is like all about the long run. If the restaurant runs this lunch promo on many days, the number of customers it takes to get the first free order would typically vary by about 12.5 from the mean. And that's it for geometric distributions. Thank you so much for watching. Have a great day.